everyone, welcome back. We were last time solving some problems from gas dynamics from the point of view of stationary shocks. This time we are going to move on to moving shocks. We just want to solve problems with shocks that are moving, okay, and that will give you a little more physical feel, which will directly lead us into going to oblique shocks. That is where we are going to. Okay. So, the first problem we want to solve is this. I am given that I have a 1D duct and it has stagnant air, pressure 1 bar, temperature 300 Kelvin, and I said air, so gamma equal to 1.4. This is stagnant air in this duct, and I am told that there is a shock and it is moving, and behind the shock pressure is 4.5 bar. Now, I am supposed to find the shock speed and the speed of the gas behind, everything with respect to the duct, the outside reference frame. Okay. So, that is the basic problem. So, to characterize the shock, what should I do? Basically, I have to just start looking at the problem and immediately say, okay, the information given about the shock happens to be pressure P2 divided by P1. P2 by P1 is given for us across the shock. No other information is given across the shock. So, the only information about the shock is P2 by P1 is given to be 4.5. Now, I will go to my normal shock tables and look at gamma equal to 1.4 page, and we will find that P2 by P1 equal to 4.5 occurs for Mach number equal to 2.0, basically Mach 2 shock, that is what we are having. Okay. So, now we have shock strength. Once we have this information, I do not want to really solve the problem in this coordinate system. We know that this is V equal to 0, V1 equal to 0, V2 we are supposed to find out, and shock speed Ws we are supposed to find out. That is the basic problem. So, I want to find in the other coordinate system, I will draw it here, shock fixed coordinate system. I am going to have a U1 and a U2, and now I want to follow one convention for velocity vector direction. Okay. I want to follow the convention for the original problem. So, I am going to say this U1, this is supposed to be negative velocity, we will keep it that way. We switched from that coordinate system to this coordinate system, and I am going to say U1 is going to be negative, okay, because it is going this way. I am saying V2 is positive, Ws is positive. That is the way we are going to solve the problem. Keep one convention, it will not confuse you, it will be very easy to solve, you will never get into trouble. Okay. Now, I want to find U1, U1 is going to be minus of M1A1, right, because it is stagnant gas, it is like a bus travelling against somebody stationary. What is the speed of this person with respect to the bus? It is the same velocity the other direction. So, I just directly minus M1A1. This is going to be equal to minus 2 into square root of gamma RT 1.4 into 288.6 into 300. Okay. Just so we want to use this number again and again, I will give you value for A1. It is 348.2 meter per second, and so my U1 is minus 2 times that, which is 696.4 meter per second. This is my U1 that is given. Okay. In a way it is given because P2 by P1 was given, from there I found M1. I do not want to call it M1, I will call it M of shock. And so, I am going to get to this point. We have solved up to this point. Now, we will go and write the equations which we already wrote before. u1 equal to v1 minus ws and u2 equal to v2 minus ws. This is the transformation between the two coordinate systems. Okay. These are the expressions which are going to be used always in solving moving shock problems, very easy to solve this way, and we know in our case v1 equal to 0, and this information has already been used. Okay. We already found u1. Now all I have to do is substitute that inside here, and then now I am going to have set of expressions to solve for. Okay. Or instead of that I am doing it some other way. Let us just go for this. v2 minus v1 equal to u2 minus u1. For me to write this, I should have one coordinate system direction for all the velocities. If I picked u1 to be positive in the other picture, let us go back here. If I picked u1 to be positive here, then u1 minus u2 will be positive, because u2 should be less than u1 in a stationary shock condition. So u1 minus u2 will be positive, but in here v2 is greater than v1, because the shock is moving, that is what is telling the gas to move this way. So this will be positive velocity, v2 minus v1 is positive, and here u2 minus u1 is negative. This kind of problems will come up if you do not take care of the sign of velocity. So always keep the sign information. I put an arrow this way, so I am going to call it negative velocity. Keep it that way, it will help you solve the problem easily. Okay. Now I can rewrite this as minus u1 times 1 minus u2 by u1. u2 by u1 will not be affected. Why? Both the velocities are negative, ratio will not get affected. Okay. Both the velocities are negative in shock fixed coordinate system, so things will just work naturally, no problem for us. Okay. Now we can just start solving the problem. How will I know u2 by u1? I can get it from rho 1 by rho 2, right? u2 by u1 is equal to rho 1 by rho 2 from mass conservation across the shock. How will I get rho 1 by rho 2? P equal to rho RT or rho equal to P by RT. I will write it like this, where this R is specific gas constant. Of course, you do not need it in ratios, but anyway I am telling you. Okay. So rho, so I will write it as P1 by P2 into T2 by T1. This is all I will get it to be. Most of the gas tables, the compressible flow tables or gas tables, none of them will give you rho 2 by rho 1 across a shock, because they already have given you P2 by P1 and T2 by T1. They do not need to give this separately, one column, just waste of paper if they give it. Okay. They will never give it. So all I have to do is just go to that particular condition, which we know it is not very difficult. We know that it is Mach 2 now. I have to go to that particular row which has P2 by P1 equal to 4.5 or M1 equal to 2. That condition, I will find T2 by T1 value, that happens to be 1.687, and divided by P2 by P1 value, which we know it is given in the problem 4.5. Okay. And this number comes out to be 0.375. Okay. So basically it is coming down to 1 minus 0.375. Now I know minus u1, we just calculated u1 to be 696.4. Okay. So v2 minus 0 equal to, I put 0, v1 is 0 for us, 696.4 into 1 minus 0.375. This becomes your expression. Now we can just directly solve. v2 comes out to be 435.3 meter per second. Okay. Now have I found the shock speed? Yes, because from this expression minus u1 happens to be the ws. Minus u1, we already put a number here. Shock speed happens to be 696.4 meter per second. It is positive, which says it is moving towards the right, from left to right. Okay. v2 is positive, its velocity is from left to right. So if I go back to the picture and say what is happening, I am going to say the shock is moving at 696 meter per second, and the flow behind it is going at 435 meter per second. Okay. That is what is the final outcome of this whole problem. Okay. We will go and look at another problem with a little more modification. Okay. I called this one problem A. I want to refer to this problem again, so we will call this one problem B, okay, where we want to say that V1 is non-zero. It is given to be 100 meter per second, exactly same problem. P1 equal to 1 bar, T1 equal to 300 Kelvin, gamma equal to 1.4. It is air, so R is also 288.6. There is a shock moving, and P2 is given to be 4.5 bar, same problem as before, except for V1 is given to be 100 meter per second from left to right. That is, there is a velocity here already. Now we are supposed to find the same thing. What is the value of V2 and what is the value of shock speed? These are two things we want to find. Okay. Just an extension to the previous problem. Now we have one variable non-zero, that is all. Okay. I picked the same number so that I can go a little faster. I can use the same A1 value. Okay. So I will just put A1, otherwise you just have to calculate square root of gamma RT, 348.2 meter per second. Okay. Now I will go and write U1 equal to V1 minus Ws. I told you this is the expression we keep on using, we will use this. Now we have a V1 that is non-zero, previously it was 0 in the previous problem. Okay. Now I have to go and find out Ws. Ws will come out to be, I will take it the other way, V1 minus U1. Okay. And now this is going to be V1. Now you have to be a little careful. In shock fixed coordinates, I will draw another picture here. This is U1 and it is having a value M1A1, right, in shock fixed coordinates. Now I want to make sure that when I use this problem I am not going to be messed up. Yeah, I want to use it correctly. One way of doing it like this, after that I will tell you another method, both should match exactly. Okay. So I am looking at this problem and I am going to say I have to put U1 as a minus of M1A1. Why am I putting this minus sign? I already did this in the last problem also, but I did not specifically tell this clearly there, but here I have to tell it. It is going from right to left, that velocity is negative. Okay. If it is left to right, that is positive for us. So I have to be very careful. M1A1 is the magnitude of the velocity, it does not tell you the direction. So I have to be very careful and put a direction minus M1A1. Okay. Now I will substitute that, so it just becomes M1A1. If this value comes out to be positive, then the shock is moving to the right, from left to right. Okay. That is the way we are going to do it. Another way to look at the same problem, I will get the same answer from another method, I will tell you that method also. Okay. Imagine this 100 meter per second flow is like a river flowing, okay, and the shock is moving on the river, or it is like a boat going on the river. Okay. If I think about it that way, there is a boat moving with respect to the water in the river and the water itself is moving. So the actual velocity of the shock from outside, or actual velocity of the boat for somebody who is standing outside, will be velocity of the river plus the velocity of boat with respect to the river, right. So it will come out to be that M1A1 plus the velocity of the river, that happens to be this 100. That also will give you the same answer, V1 plus M1A1. Okay. It is just a cross check, I do not need to do it two different methods, one is enough. If you just follow the math, it will come out to be right, as long as you do not make any mistakes. Okay. So now we just find this number it is, we know that m1 is 2 because p2 by p1 is given to be 4.5, it is the same value. So, I am going to say it is 100 plus 2 into 348.6 point, I think it is not 6, it is 0.2. The answer comes out to be, it is almost the same answer, 696.4 was the previous answer plus 100, 796.4 meter per second. This is the answer you are getting here. Okay. Now, I want to go and solve V2 now. Similar to this formula, we have a V2 formula, U2 equal to V2 minus Ws. Okay. So, how will I find my U2? U1 into U2 by U1 at m equal to 2, easy way to do it. Okay. Gas dynamics people like this a lot, cancelling ratios, very nice way of doing things. It works great for us because in all compressible flows tables and all gas tables whatever you pick, they all give you only ratios. So, I have to multiply all the ratios to get to whatever number I get. Okay. So, I know this U1 value, it happens to be minus 696.4, this multiplied by U2 by U1 I want to find out. U2 by U1 we already found out from the previous problem, it is the same value, it has to be T2 by T1 divided by P2 by P1, that we found out to be 0.375. Okay. If I do this, this is just U2, now I have to find V2, so I will write it V2 equal to U2 plus Ws. Remember the minus sign, if you do not use the minus sign things will go wrong. Okay. Minus 696.4 into 0.375 plus 796.4. Okay. This is what it comes out to be, and the answer happens to be 535 meter per second. Okay. This is what you are getting. Now, I want you to compare problem A and problem B. Okay. I will make a small table. V1 for problem A was 0, V1 for problem B was 100. Okay. Ws 696.4 and here it is 796.4. Okay. V2 435, here it is 535. Okay. These are the numbers we are getting. Okay. If you go look at U1, U2, those numbers will be different. Okay. Other numbers, if you look at it, they seem to be matching very nicely like this. In fact, every number will have this 100, it so happens that it will be that. Okay. Now, is this logical? Is this going to be just this? If I have a V1 some value, I just add it to all the values and it will come out to be this answer always? That is the question we want to ask. Okay. It so happens that for this type of a problem, yes it is. Why? That is the question we want to ask. Okay. Now, we will go to that side and start drawing pictures, more pictures. Oh, I have all the pictures I need, it looks like. I have all the pictures I need. This was problem A and oh, problem B picture I have to change. Okay, sorry, I have to draw new pictures. Problem B. am putting 696, it was 696.4, that does not matter so much for us. If I draw this picture, it becomes easier for us to understand the problem. Okay. If I look at the picture from problem A, I have this case, and if I say I have an observer standing here and he is observing this particular problem. Now, if I say he is not just standing there, but he is moving this way with 100 meter per second, he is on a bus. If he is moving like this, what will he see as this velocity? 100 meter per second. What will he see this problem as? 696 plus 100. What will he see this? Plus 100. That happens to be this problem exactly. Okay. It is just a shift in coordinate system. Okay. The person who is watching is moving, that is the only change if you look at it. Moving shock problems, mostly it will come out to be something like this. It is easier to work with. For a given strength, there is a particular delta u you will get. If they change just this variable, all I have to do is add that number everywhere and the problem is solved. You do not need to resolve the problem. That is assuming you have already solved the problem once for one particular V1. If they change just V1, very easy to solve, just add it. Okay. That is all it is supposed to be. Now, we will go to next problem. Continuing the numbering, I will call it problem C. Okay. We will continue the same problem in a way. I am going to say the shock is going like this and it reached the wall. There is a wall at the end, it should be a straight line. There is a wall at the end. Okay. So, what is happening now? There is a shock, it is going like this, and there is a flow coming here. What was the velocity there? We will pick the problem A, okay. 435 meter per second, this is V1 equal to 0, V2 is this, and this value was 696 meter per second, whatever. Okay. Now, this problem does not change till the shock goes and hits the wall. After that, the shock does not have to tell any more gas. What was the job of the shock? It has to go and tell everybody move that way. Okay. And it has told all the gas that is present in the tube, its job is done, it vanishes. But now there is a problem. What is the problem? We will go to the case where the shock has reached the end. So, I will draw one more picture. There is no V1 equal to 0, every condition is all this value, all the gas is moving with 435 meter per second into a wall. Now, there is a problem, things cannot go just through a wall stops all the flow, which means now there should be a new shock created here and that has to be moving against this flow, this is going like this, such that the velocity behind it is supposed to come to 0. That is the job of this shock. This shock is going and telling, this is what they call the reflected shock. Okay. This shock's job is to go and tell every fluid that is coming this way that there is a wall, you cannot move this way. So, what will happen? All the people thought, all the molecules actually, we will go back to molecules, all the molecules thought there is a lot of space, they are all coming this way. That is what this shock told them. When this shock went here, till that point there was no information about this wall to this fluid. So, they all kept coming. When the first layer of fluid that touched this, when the shock touched happened, immediately after that, that fluid knows that there is a wall there. So, it tells every other fluid this way coming in that do not come in this way, there is a problem here. That information is going this way. What will happen? This is inducing a velocity this way. In a way, it is slowing down this fluid coming to the wall. That is what is happening here. Okay. This is the physical field. Once you have the physical field, problem is easier to solve. And it has to come to V equal to 0. Okay. That is what we are trying to solve. Now instead of looking at the problem with shock going right to left with all velocities negative, I will just go look from the behind of the board. What will it look like? I will just transform this problem to, I turn the board the other way and look at it from the other side, okay. Then it will look like this is the problem we are going to solve. Here I am given V1 and V2, both the values are given. I am renumbering things, okay. It is no more connected with problem A. I am renumbering it here V1 and V2. This old numbering I will remove, okay. Do not get confused with these numbers. This is the problem we want to solve now. We are supposed to find what is the speed at which the shock goes. Okay. So let us go and find out how to do this. So again we are going to write the same set of equations. We will say u1 equal to v1 minus ws, u2 equal to v2 minus ws. Remember, there is no compressible flow tables for moving shocks. So we have to do this transformation of coordinates every time to go to stationary shock case and then use the tables, come back to moving shock problem. Transform to one side, come back, transform again. Okay. We are now given V2, this happens to be 0 and V1 has a value 435 meter per second, that is given to us. So I will again go and write V2 minus V1 equal to U2 minus U1. Remember to keep the velocity directions important. If it goes negative, if it goes leftward, it is minus sign. We will keep that into account. Okay. So V1 minus 435 meter per second. Okay. I will write it here. I have put an arrow on 435, so that we do not want to touch that. Okay. I will change it only here. V1 equal to minus 435 meter per second, which means it is going right to left. We will keep it that way, and V2 is 0. So I am finally getting it to be this side 0 minus 435 will be 435 equal to, now I do not know U2, I do not know U1, okay, and I am supposed to guess Mach number of the shock or P2 by P1 of the shock. So you have to work through with this problem only. Okay. How will I do it? Okay. Let us say I will write U2 as minus M2A2. Okay, remember minus is coming because in my shock fixed coordinate it is going from right to left. Similarly, I will do for U1, it will become a plus M1 A1. Do I know A1? Yes, I know A1 because I found the temperature here. T2 by T1 was known, right? For the problem A, T2 by T1 was I think 1.68, something like that. Okay, which oh, I did not give you that part of the problem. Okay, anyway, I will just do it right now. (300 into 1.687). We wrote this T2 by T1 value before, in fact in this page, in fact it is slightly shown here. Anyways, okay. So from there I will get a A1 value. I have to find square root of gamma RT, and that comes out to be 452.2 meter per second. Okay, you get it to this value. We know up to here. I do not know M1, but if I know M1, I will know M2. Okay. Now A2, can I write in terms of A1? Yes, I can. We will write it that way. M1 A1 minus M2 A1 into square root of T2 by T1. Can I write it like this? Yes, okay, because A2 by A1 is just square root of gamma RT2 divided by square root of gamma RT1. So I can simplify it to this. So what I did is A2 is equal to A2 by A1 times A1. again the favorite multiplication of ratios, gas dynamics people. Okay. So, now I have this, I do not know M1, I know A1, I know A1, I do not know M2, I do not know T2 by T1, but if I know M1, I will know M2 from normal shock tables, I know T2 by T1 from the same row normal shock tables. Okay. So, if I know M1, I know this whole expression, okay, and then now I have to see whether 435 is matched. So, it is now a problem of iteration. I have to guess an M1 and see if 435 is matched by this side, okay, and I keep on doing this till I solve the problem. I will start guessing M1 one value, next value till it solves. Okay. Instead of writing it like this, we will rearrange this and write it a little better. I will go to the next section. It so happens that for most of the problems it will be this, delta V by A1 equal to M1 minus M2 square root of T2 by T1. I will keep getting this always in most of the moving shock problems where I do not know the shock strength. The previous problem section A and B, when we solved, we knew the P2 by P1 for the shock. So, it is very easy to solve. Here we need iteration, okay, but this is the general form where delta V is V2 minus V1, okay, that is what you will have. Now, we will get to numbers. So, I will take this also to that side. I will write a function that looks like M1 minus M2 square root of T2 by T1 minus, I know delta V was 435, I know A1 is 452.2, I will get that number to be 0.962 equal to 0. So, I have to form a table for iteration M1, M2, T2 by T1 and the whole thing, I will call it left hand side. Okay. So, we have to start guessing, each column will be one guess. I will start guessing with mark number 2 and I go to normal shock tables, gamma equal to 1.4 and I look for M2, that is 0.577. T2 by T1 happens to be, we already know this number, 1.687. Now, if I do this calculation on the left hand side, that number comes out to be 0.285. I do not know how to guess the next number, okay. I will generally guess 3. I could be having to guess less than 2 or more than 2, I do not know, I say I choose 3, we will see what happens. This number is 4.475, again normal shock tables, gamma equal to 1.4 for mark 3. This number is 2.679 and this is 1.26. So, it looks like I went the wrong direction, I guessed wrong, okay. I should not be guessing from 2, I should have guessed lesser, I guessed more, the number went the same direction. Okay. Most of the functions in gas dynamics are monotonic, it is a good thing for us, okay. That is what is used here. Now, I will go guess something lesser, okay. This is very close to 0 and when I go from one number increase it is too high. So, I will guess something very close to this, but lesser, something nice. I will start with 1.5, that number is 0.701, 1.32 and now my left hand side comes out to be minus 0.267. Okay. Now, I know the answer is between this and this, I just have to guess a number in between. Okay. It so happens that in my gas tables there is no 1.75, okay. My gas tables has 1.7, 1.72, 1.74, 1.76. So, I thought okay, I will pick 1.7. Okay. I am still guessing, I am not interpolating. I could have interpolated and got to the answer faster. I got this answer which says I should go more towards 2. Even now I could interpolate, but it is so close that we will just try the next number in the next row in my gas tables, okay. That is easier. So, I will go 1.72, this is 1.70, okay. The next one is 1.72 and that number is 0.635, 1.473 and this number comes out to be minus 0.013. It is even close, but still the same side. So, if I took a interpolation, probably I would have been a closer match. Okay. I do not know, I am guessing, so it comes out to be this. I could have picked 1.74 instead of 1.75, I picked 1.7. Okay. Now, we will look at the next one, 1.74, I am moving the correct direction, 0.631, 1.487 and this number is 0.008. This is the closest I could get and I have crossed. If I want, at this point I could interpolate between these two to get to a closer answer, which will probably be 1.735, which if I approximate to second decimal, the answer is 1.74. Okay. So, this happens to be my Mach number. Typically in gas dynamics, if you guess right at the initial conditions, you will solve in the 6th or 7th iteration, okay, most of the problems, unless you start with say Mach 20 and slowly decrease every 2, then you will take so many iterations to get to the answer. Okay. So, once I know m1 equal to 1.74, I will go and find Ws. We had the formula already on the board before, so I will just write it. This you know how to derive it from two different methods. Okay. This number happens to be 351.8 meter per second. This is the speed with which the shock moves with respect to outside observer, with respect to the duct, okay. And P2 by P1 for this shock is 3.336. Okay. Now, we will again observe stuff. Okay, I have numbers. Oh, anyway, I will erase and do it first. Problem A, we had a case where the shock is moving this way, P1 equal to 0, this was 435 and this was 696. And now we are saying it went and it found a wall, and so that becomes your what was this problem? Problem C. Problem B I said? I did not erase B probably here, it is not problem B, we are working on problem C I think. Okay. So, I just did not erase that part. Anyway, problem A said this. Now, problem C, it says, now this is the velocity here. Now, I am thinking about a shock going this way and the flow incoming is 435 meter per second, V2 is 0, okay. And when the shock goes this way, it is going with velocity we just found 351 meter per second, 350, it is close to 352 meter per second. We are not interested in the actual number, I just want to tell you the trend. Okay. Here P2 by P1 was 4.5 and here P2 by P1 is 3.36, sorry 3.336, some such number. I could have written as 3.34, that is enough. Okay. So, what we are finding is, when a shock goes first, it is having some particular pressure ratio and then it is created a supersonic flow. Actually, it was not supersonic, was it? M2 we did not calculate. I think I calculated, I did not do that part for you people. M2 was 0.577. It was not supersonic really, the temperature is also high. Velocity is high and temperature is high, it is still subsonic flow. Okay. Because the velocity, the speed of sound for this case A1 we picked was 450 or something like that, right, something higher. So it is still subsonic case somewhere here. Okay. Anyways, it is subsonic flow created, it is going like this and it is suddenly meeting a wall, and that information has to be transferred to the whole fluid by the second shock. It is not moving very fast as this one, it is moving slower, but wait, with respect to the fluid it is actually moving very fast. With respect to the fluid, if I think about it, it is going extremely fast. The fluid is going this way, but still the wave is going this way. It is like a treadmill, no? It is like a treadmill. The what is the thing? Belt. The belt is going this way with 435 meter per second, and the person running on it is running this way for 352 with respect to outsider, which means he is actually running the total velocity added by these two, which is 787 meter per second. Okay. The shock is actually traveling faster in the gas that is heated. The main thing is the gas is hot, okay. It has been heated by the first shock, so it is traveling very fast, but when it reflects it does not need such a high strong shock for it to tell the fluid to stop. That is the main thing here. Previously it was going with 4.5, now it is going with 3.336, that is enough. Okay. With that it can say stop, there is no more movement needed. Okay. That is the information taken by this shock, that is what it is carrying. Overall problem, if you look at it, I had a duct, I had 0 stagnant gas initially, there was a shock sent in P2 by P1 4.5, it created a flow of 435 meter per second this way, and then it stopped, okay. And that information is carried by this, and then every gas that is processed by the second shock will come to stop, it will not move anymore. What happened to the overall gas that was initially sitting in this whole region? Now it is compressed and it is sitting in a very small region here. That is the other thing that you have to think about. Okay, if I think about, let us say I will pick this whole volume, that whole volume is probably now sitting in this small area here, that small volume here. Why? That gas was compressed twice, once by this, once by this. So overall, if I want to call it P3 by P2, then I can say the net final pressure is 4.5 times 3 of the order of 14, okay, of the order of 14 times compressed. So the volume will be 1 by 14 of that roughly. Okay, it need not be that because temperature is also changing, okay, but it is roughly that. So all that volume is now only here, all that gas which was initially there. Okay. Let us say if I had this gas as some colored gas, all that color will be only inside this small region. What is here then? The gas that was in this volume here, like that it gets compressed on the other side. You have compressed it twice with 2 different shocks. Okay. I guess I will not be able to complete problem D fully, we will see how much ever we can go. If needed we will stop with the iteration part. Okay. We will go to problem D. I can take a shortcut a little bit with using the expressions from before, we will see. It is almost problem C, except for I am picking a particular velocity. This is a case where I am having a flow through a duct 20 meter per second. I am having a simple flow through a pipe 20 meter per second, and suddenly somebody puts a lid on it, they close the flow. Okay. I want to find what happens inside the duct now. Okay. This is the unsteady problem, we are trying to solve an unsteady problem already. Okay. What is going to happen? All this flow has to be stopped because there is a lid that is closed and says no more flow through it. Okay. So there has to be a shock that is going this way, and V equal to 0 should be enforced then by that shock. That is the goal, right? That's what is the goal of this particular shock. It is going to do that job. Okay. let us say we know this T1 equal to 300 Kelvin temperature here, V1 equal to this, and this means that A1 equal to 348.2 meter per second. I am using same numbers so that it is easier. Okay. Now, we do not like solving the problem from right to left, we are always using left to right. So, I will transform this to a problem of this type, and I am going to say there is a shock that is moving left to right, and its job is to make V2 equal to 0 while V1 was having a minus 20 meter per second velocity. Now, I am putting correct direction, okay, minus 20 because it is moving the other way. Okay. So, V2 minus V1 equal to 0 minus of minus 20 meter per second. This is also equal to U2 minus U1, U2 minus U1. Okay. So, we want to solve this. We also know this. We wrote the expression in different forms, now I am writing another form, that is all. Okay. Actually, I do not need to do all this, I will just we do not want to derive the whole thing, I will take the expression from below. We from the previous time we wrote this, no, delta V by A1 is equal to M1 minus M2 square root T2 by T1. I can use this directly, I do not want to go derive this whole thing for you. Okay, it is same problem as before, except for we gave a new dimension to the problem. We said it is an unsteady problem, suddenly there is a wall that appeared in the duct. Okay. After that the problem is exactly the same, that way I will cut short and finish it off in this 2 minutes left. Okay. So, what do? Exactly same procedure. Okay. Delta V is given to be 20 meter per second, A1 is given to be 348.2. So, I will get a number for this, that number is 0.057. Okay. So, I just have to solve this problem with this expression M1 minus M2 square root T2 by T1 minus 0.057 equal to 0. This is my left hand side and I just want to solve this problem. Again I have to go and guess, that is the same thing, I have to go through the same guessing process. We will again go form the same table, I do not want to write below, so I will go to the next page. Again I always like starting with M1 equal to 2, so I will start with that. In fact, I remember this number 0.577 also. This gives you a left hand side of 1.19 while it is supposed to be 0. So, I am guessing too bad. Now, I have experience from the previous problems, I know if I increase Mach number left hand side increases. Okay. So, I will decrease immediately. Okay. Let us say I will guess something low, 1.4, okay, because too high I am going more. I cannot guess 1, okay. If I guess 1 things will go wrong. It will not go wrong very much, just go back here. If I guess 1, what will happen? What will be the M2 value? It will also be 1. Okay. What will be the value of T2 by T1? No change, it is a Mach wave. T2 by T1 is also 1. So, 1 minus 1 will be 0 and it is minus 0.057. Now we look at it, it is very close to 0. So, I should not be guessing 1.4 really. Okay. I should be guessing something close to 1 so that I will get to the answer. Okay. We will do that. Instead of 1.4, I was not thinking like this when I was doing the problem on paper. So, I will start guessing 1.1 here. I skipped one column in my guess. 911, 1.065, and this comes out to be 0.103. This is what we have here. Okay. And I know if it is 1.0, we know the values. It is we just did this, no, 0.057. We know this also. So the answer is somewhere in between this, probably very close to 1. Okay. Now I just have to guess. Let's say I'll in my tables I have only a set of numbers. I'll get 1.02. That's the closest I can get to 1. I have 0.981, 1.013. That gives minus 0.024. I want to go even closer. Okay. So I have to increase from here a little bit, go 1.04. .962, 1.026, and this number comes out to be 0.008, which we will say is approximately 0. So I am getting my Mach number to be this. Okay. For if I stop a 20 meter per second flow in a duct with a sudden lid completely closed, no mass flow through it, then I will produce a 1.04 Mach number flow, Mach number shock going against the flow. Okay. That is what we know as of now. We will go and find the implications of it next class, because I have one more full page of implications because of this. Okay. We cannot go through that now. We will stop here. We will just stop with m1 equal to 1.04. We will come and continue the same problem next class at the beginning. After that we will do one more problem and then we will go to 2D problems. Any questions you have? It is an easy way of solving if you just remember that one formula and just iterate. See you people next class.